Hello, this is Dr. David Kreller of the Department of Chemistry of Chulalongkorn University in Bangkok, Thailand, here with another video lecture. In this video, we're going to be talking about how to calculate a titration curve. We are going to calculate pH as a function of added titrant in the titration of 40 ml of 0.03 molar sodium hydroxide. That's going to be in this beaker below the burette which contains 0.05 mole per liter HBr. The first calculation you should do whenever you are doing calculations for a titration curve is to calculate the volume of the titrant, which here is HBr, which is required to reach the equivalence point. Of course, you're going to be doing calculations for a variety of volumes of titrant that are added up to the equivalence point and past the equivalence point. But a good thing to calculate at the very beginning is the volume of titrant needed to get exactly to the equivalence point. And that will be an important reference as well for some of your calculations. Let's see. So we have sodium hydroxide titrant. So the first thing we'll do is, this is a stoichiometry calculation. We'll calculate the number of millimoles of sodium hydroxide by multiplying the volume of it times its molarity. Then it's a stoichiometric conversion. We now have the millimoles of NaOH, but let's convert that to millimoles of HBr. But it's just a one-to-one stoichiometry here, easy conversion. And we'll multiply that by its molarity in this case, and we'll end up with volume in milliliters of HBr, which must be added to get to the equivalence point. So let's keep that in mind. It will take 24 mil to get to the equivalence point. There's three regions of the titration curve, and each region kind of requires its own type of calculation or thinking. Okay, before the equivalence point, i.e. up to 24 mil, there's one type of calculation needed. Then at the equivalence point, there's a special sort of line of reasoning we'll follow to predict the pH at that point. But then there's some more calculations that are required after the equivalence point, and those are different than the calculations before the equivalence point. Slightly different, but completely understandable. Okay, let's quickly do a calculation of the pH at the very start of the titration, i.e. the pH when the volume of titrant that's been added is 0. That's a very simple calculation. It's just a basic solution, and the concentration of the base is just going to be equal to the concentration of the sodium hydroxide that you have at the very beginning. So take that concentration, 0.0300 moles per liter, take the negative log of that, but that will give us a POH. And to calculate pH from that, it's just 14 minus POH, or 14 plus the log of that number. It's just 12.48. Now quickly, a couple words about the nature of the calculations of pH before the equivalence point. So we still have a basic solution. We will have a basic solution all the way up until the equivalence point. At the equivalence point, they will have neutralized each other, the acid and base. But before the equivalence point, there's leftover base. Some of the base has reacted with the hydrogens. The hydrogens that have been added, hydrogen ions, will react completely with the hydroxide ions that are present in the solution. And of course, we know something about the chemical reaction by which they will react. Hydrogen ions and hydroxide ions react to form water molecules. Actually, if we write it this way, with water molecules as a product, we know that the equilibrium constant is 1.0 times 10 to the 14, the huge equilibrium constant. One way of knowing how big that equilibrium constant is for that reaction is just thinking that, okay, this is actually just the opposite reaction of the autoionization of water, which has equilibrium constant Kw, 1 times 10 to the negative 14. But we've reversed this reaction. We have to take the inverse, or the reciprocal, of the equilibrium constant. But anyway, the point I want to make is that the hydroxide ions that were in there and then will react very completely with the hydrogen ions that you add from the HBr. And so the amount of hydroxide that remains in solution is controlled by the volume of the titrant that was added. So the calculation is the number of moles of hydroxide that are remaining is equal to the number of hydroxide millimoles, I guess, that you started with, minus the number of hydrogen ion millimoles that have been added. So the number of millimoles of hydroxide will be its initial volume multiplied by its concentration. Then subtract the number of millimoles of hydrogen ions. And after 3 mil, for example, have been added, 3 mil times 0.05 mole, that number of millimoles will have been added. So once we subtract that number of millimoles of hydrogen away from that initial number of moles of hydroxide, we get 1.05 millimole in this example. But for the pH calculation, we need a concentration of either hydrogen ions or hydroxide ions, from which we'll calculate pH or POH. Okay. Let's calculate hydroxide ion concentration. That's what we have, 1.05 millimoles. We'll divide that number of millimoles by the total volume. 40 mil started with, added 3 mil to that. Total is 43 mil. So divide 1.05 by 43, get 0.0244 moles per liter concentration of hydroxides. And again, pH is just 14 minus the POH. So it's 14 plus the log base 10 of that concentration of hydroxide. Get 12.39 for that first data point.
I'm going to quickly jump over here to Microsoft Excel to show you a spreadsheet that I set up to help me do the calculations. So you see the results of the calculations here, and I've color-coded these regions of this page of the spreadsheet. Yellow for before the equivalence point and blue for after the equivalence point. You see I've set up a variety of volumes of the HBr that have been added. I've calculated in separate columns the number of millimoles of sodium hydroxide, and the number of millimoles of HBr. You see the number of millimoles of NaOH is constant because that's controlled by the initial concentration and volume of that titrant solution. But the number of millimoles of HBr is variable and increases as we add higher and higher volumes. Then I also calculate the total volume. And then finally I calculate pH. I subtract, just like the calculation I showed in the PowerPoint file. I take the initial moles of hydroxide, subtract the number of, millimoles, subtract the number of millimoles of hydrogen ions to get that concentration of hydroxide ions that are remaining. But I divide that by the total volume. Then I take the log base 10 of that to get the POH and then calculate pH. So here's my calculations for those remaining points before the equivalence point.
We've gotten ourselves to the equivalence point, where the equivalence of hydrogen ions that have been added is completely equal to the equivalence of hydroxide ions that you start with. And you know that they react with each other completely. A huge equilibrium constant, 1 times 10 to the 14th. Basically, completely wiped out. They're gone. All you have left is water. But for calculation of pH, negative log of hydrogen ion concentration, you need hydrogen ion concentration. So what's the hydrogen ion concentration in pure water? Well, we know that due to the ionization of water, pure water is creating hydrogen ions and hydroxide ions, actually. And if the solution is neutral, the hydrogen ions and the hydroxide ions have equal concentration of 1 times 10 to the negative 7 moles per liter. So when the acid and base have completely annihilated each other, and all you have is pure water and some salt, actually, as well, you do have some hydrogen ions being created by autoionization of water. And so the pH will just be the negative log of that concentration. And so negative log of 1 times 10 to the negative 7 is the negative of negative 7. So the pH in the strong acid, strong base titration, or strong base, strong acid titration, either way you configure the reaction of the strong acid and strong base, the pH will always be 7 at the equivalence point. That's something that I see a lot of chemistry students kind of memorize. Oh, pH 7 at the equivalence point. Well, there's a reason for that in the titration of a strong acid and a strong base. As we'll see in a future video when we look at the titration of a weak acid with a strong base, or the titration of a weak base with a strong acid, the pH at the equivalence point is not 7. It's only conveniently 7 in this strong acid, strong base reaction. Now we're getting close to the end. Now let's look at the calculations associated with region 3, the region after the equivalence point. Okay, we started off with strong base in solution, to which we added strong acid. We reached the equivalence point. Now let's add a little more strong acid. Okay. Now we have more hydrogen ions in solution than hydroxides, and we have an acidic solution. Okay, how many hydrogen ions do we have left in solution? Well, that depends upon the volume of the HBr in this reaction that we've added. As we added more and more HBr titrant, we have more and more hydrogen ions left over in solution. And so the pH will be controlled by the total number of millimoles of hydrogen ions that we have left over, but it will also need to factor in the total volume, because the volume of this solution in which the pH is being measured just goes up and up as we add more and more of the titrant. Okay. So now we'll do a sample calculation considering the point at which we've added 25 mil of HBr. Okay, let's calculate the pH at this point. Remember, we used only 24 mil to get to the equivalence point. So here we are 1 mil past the equivalence point. So the calculation has the number of millimoles of hydrogen ions that have been added, subtract the number of millimoles of hydroxide ions that were there initially. Okay, so the number of millimoles of hydrogen ions that we've added will be 25 mil times the HBr concentration. Okay, and then subtract the initial number of millimoles of hydroxides that were there. That's 40 mil times 0.03 mil. Calculate this with the subtraction, we get 0.05 millimoles of hydrogen ions from the HBr left over. Not very many, because we're just slightly past the equivalence point. Okay, but for the calculation of pH, we need the concentration of hydrogen ions. So we take the number of millimoles of hydrogen ions that are left over, divide that by the total volume. 0.05 millimoles divided by now 65 mil, because that's the total volume. When we've added the 25 mil of HBr titrant to the initial 40 mil of NaOH titrant that were there initially. So there's a concentration of hydrogen ions, but we need pH calculation. So now we don't have to go via POH. We can just take that concentration of hydrogen ions, take the negative log of it, and when we do that, we get 3.11.
Now, I'll just quickly go back to the Excel spreadsheet because I also used it for the calculations past the equivalence point. So here's the volumes past the equivalence point for which I did the calculations. Okay, so calculated the number of millimoles of sodium hydroxide. Again, that's still the constant. That's the amount of sodium hydroxide that we started with. But the number of millimoles of HBr keep going up and up as we add larger and larger volumes. Okay, so but now the calculation is moles of HBr subtract the number of millimoles of NaOH divided by the total volume, and just directly take the negative log of that to get the pH.
Here we are with our finished product. Here's the titration curve, the curve of pH as a function of volume of the titrant added. You understand this entire curve. Good for you. A couple things I want to point out. So you can see just how rapidly pH is changing around the equivalence volume. Well, chemists are very much aware of this big change in pH, and actually that's the basis of how pH titrations are used. So whether chemists are using indicators to detect the endpoints, or using automated methods, like using some kind of instruments that automatically do titrations, that big change in pH as a function of volume of titrant is taken to advantage. And a future video will study the way that pH indicators work in the context of that big change in pH. Okay, thank you for watching, and thank you for learning.